Okay, so we posed the question, if you got 2 points on the graph and want to do an exponential model, as long as the points are on the same side of the x-axis, you can do it. Now, an exponential function always stays on the same side of the axis unless you vertically shift it, okay? Incidentally, if you get thirsty, you only got to get the pot over there. Seriously, you're welcome to take one of those. Bought it for Thanksgiving, a bunch of people over, we don't drink them. Over here, a little bit of history. About 5 years ago, I drank this much of this Mountain Dew and haven't had anything artificially sweetened since. I haven't had any Mountain Dew since. I'll figure out a way to work that into the review, okay? Because you can consider what happens if you take one of those and shoot a hole in it. They're not going to shoot a hole in it. They got some recent laws. We're not allowed to discharge firearms on campus. Not even supposed to carry them. Yeah, we're a little sensitive about that, especially since the shootings several years ago up the road at Virginia Tech. Okay. Anyhow, exponential model given 2 points, excuse the exaggeration. 2 points have to be on the same side of the axis unless you got a vertical shift. And then that gets tricky. So we're not going to be able to solve that one algebraically. Actually, we can because by the slopes. We're not going to. Okay. How do you do it? Use one of these forms. What do you do with the form of a function when you have points on the graph? Okay, so the process, let me see where we are with the process. Okay, well, you got your numbers there. Use a lowercase b. Better form. The uppercase b, for example, occurs in the standard form that I use for switching from exponential to logarithmic and back. So I kind of save capital B for that because you're going to need it when you solve for either little b or k. Any questions? Okay, now I'm not going to go through the details of solving equations at this point because the class is going to need to see it. And when we go through these things and do the details, just, yeah, you'll see it then. And I don't know why it's still recording, but fortunately, nobody ran in front of the camera or shouted out in a loud voice. I think we're okay. Okay, so yeah. I was recording this. I forgot to turn off the recording. That's okay. Okay, so we choose a form that almost looks like two words for M. Choose for M, and don't want to confuse anybody. With that, I'll find other things to confuse you with. Okay, we choose the form. We eliminate A, and the way we do that, you solve, let's say, the first equation, whichever one it is. It's this when you solve it for A. And then you plug that solution in here. When you solve this for A, you're going to have a number here and a number for X. And when you plug in your solution for A, it's going to be this over this. There's not going to be an A there anymore. And you just have an equation in X that you can solve using the conversion from exponential to logarithmic to exponential form. In other words, using the inverse function properties. Okay, so now linear model. Given 2 points. You could use the y equals mx plus b form. Okay. Or you could use y minus h equals m times x minus k, or you could use all kinds of forms. Form that's kind of preferable because we're emphasizing solution by elimination. Now, let me digress. When I say eliminate A, we don't use the process of elimination to eliminate A. I'll say, I have to write this small. It's going to be hard to read even on the camera, but using substitution. Okay. Don't confuse that with the process of elimination that we can use for linear equations. So, given 2 points, we're going to get the form AX plus BY equals C. Okay. So this is your form. AX plus BY equals C. You get 2 equations, you solve for A and B. It can be done using substitution. And as I've said before, if you choose to use substitution, and I don't say do it by elimination, you can. I'm going to say standard is going to be to use elimination, because if you use elimination, it means you can write a matrix model. And I would very well be likely to ask you to do something like that on the exam. Write the matrix model, write a matrix equation, or write it as an augmented matrix and reduce it. Now, if I ask you to just write it as a matrix equation, I haven't shown you. It would be easy if we had a little more time, one more day. haven't shown you how to solve a matrix equation, okay? Because you don't know how to do an inverse matrix. For a 2x2 system, the inverse matrix is very simple, but it's not that simple, okay? The point then is you can use the inverse matrix, or you can use the solution using an inverse matrix with computer algebra software, okay? Just tell us, okay, invert the matrix and multiply by these numbers, so forth. Okay, well, anyhow, we want to distinguish an exponential model from a linear model. And there's even a power function model that you should be able to do. We've done it in the past. Power function has a form y equals ax to the p. Well, again, solve by substitution. Eliminate a, etc. Very much like the way you solve this, except that in one case you have to switch from an exponential to logarithmic form, in the other from logarithmic to exponential form. Now, if I ask you to do a power function model, I shouldn't have to, I probably will tell you. Well, yeah, I'll give you the form y equals a x to the p. If I ask for an exponential model, I expect you to know what the three different forms are so you can do it and so forth, okay? Okay, for an exponential function, I don't have it write it out, but I'm going to use this space, but I'll have something to do with it later. Okay. An exponential function find the half-life for delta. Need to know how to do that. Okay. Make that and or the growth factor. Okay. And you got to understand what those things mean. Given information for growth rate or growth factor, find your model. Given a point and rate of change, find your linear model. Rate of change is just your slope. So what we're talking about here is how to get models. Now there's other stuff, there's a chapter or a section on what you do if you got a bunch of exponential data or a bunch of logarithmic data or a bunch of linear data or power function data. How you can fit a curve. Use Excel or something, but you have to use machinery to do it. We'll try to, rather than learn how to use the machinery, try to understand what's behind it all. Once you understand this, it's real easy to understand what to do with the machine. Okay, and we might talk about that, but I'm not going to be putting it on the test. So hopefully you know how to do all this. I'm bringing it to your attention. When we get into details in class, we'll do some examples, as many examples as we can of these different ideas. Okay, now the other big thing here, of course, and it's not the bottom of the board, that doesn't mean it's not a big thing. B to the C equals A, if and only if log base B of A equals C. So if your variable appears in the exponent, put your equation into this form, then switch it to this form so that the variable in this exponent C now appears here. We can get to it. We've said that many times. Okay, so we're saying it again. Or if your variable happens to be tied up in a log expression, you can switch here, and now your variable is no longer in the log. And you can use standard algebra in either case once you get your variable down into the equation where you can deal with it. Okay. Now, if your variable is here and here, you're out of luck. Okay. Then you need to be able to draw a graph and at least estimate a solution. So if your variable variable's in C, switch to the log. If your variable's A, you switch to exponential form. Okay. If your variable's in both A and C, use machinery and graph it. And you want to see what the graph looks like. So I can kind of put a little note here, variable. In A and C. use technology and or graph. For example, if you have b to the c equals a, and it's b to the 5x equals 3x plus 9. Okay, you graph e to the 5x, you get an exponential graph, and you graph, what did I say, 3x minus 9 or something like that. You graph 3x minus 9. So that in this case, what you get typically, put myself a little room here. What you get will typically give you the graph of an exponential function and the graph of a linear function. And you'd be looking for this point here. Now, it wouldn't necessarily be a linear function, could be a quadratic function, could be a power function, one type or another. Okay. There you have it. Now, there's a lot more that could be said. I would love to be able to include the calculus course because I think it belongs there, but we just can't get it done. I could get it done, but 90% of the class couldn't. But be aware, those are techniques you might want to know. That's kind of something you might want to keep on your radar screen. Another curve fit that we might well do is a quadratic model. We're given 3 points. As long as the points have different x coordinates, it has a quadratic model. There is a unique parabola, just exactly one parabola that will go through these 3 points. So let me ask you just to sketch 3 points that don't lie on a straight line, and then see if you can make a parabola through those points. Okay, for the 3 points that I drew, I would think that's a bad quadratic model because it's not symmetric. Okay? So maybe this, maybe even this, that's better. Because I'm not sure we can keep going up as we go through this point the way I drew it. Now, the way you drew your points, maybe it is possible. Not sure we keep going up through these points and end up all that symmetric, and maybe I just did a bad job of it, okay? Now, you can't really tell if you practiced it enough and solved a lot of problems and got a feel for it. You might get pretty good at it, but we're not going to do that. Just want to understand that there is a quadratic model that fits those 3 points, and we can easily find it. I'm going to ask if you want to suggest how we might do that. Okay, now we want to, if we're going to do a quadratic model, we'd better have a form. We're going to do a model based on points, exponential form, ab to the x, ae to the kx, a times 2 to the kx, linear form, ax plus by equals c. You could also use y equals mx plus b. either way, you have two parameters and you need two equations. Power function, same thing, very similar to exponential, but the solution process. You end up having to solve for the exponent, which means you're going to have to use a logarithmic form. Use AB to the x over here. You just have to take an algebraic power and finish the solution. But either way, it's something that you should be able to pretty easily do. Quadratic model given 3 points, or we're having trouble getting down specifically, but you really need to know this because we use it with the quadratic equation. It's part of the statement of the quadratic formula is very important. Okay. Now, once you get that, you're going to just plug the x and y values for each point into the form. So how many equations are you going to get? Okay, so once we know the form, and we need to know the form of a linear, power, exponential, or quadratic equation, function, okay? If your form is y equals ax squared plus bx plus c, plug in to get 3 equations, and solve using elimination of matrices. Okay. You have 3 equations. You would get a 3 by 3 matrix. And I'll just write down what the augmented matrix would look like. You're going to have 3 numbers here and a number here. And 3 other numbers and a number here. And 3 other numbers and a number here. For matrix equation, well, you're not going to have variable. I mean, you're not going to have specific numbers here. So we'll call that x, y, z. Okay. And it's not actually x, y, z. If we're using the form ax squared plus bx plus c, it's abc. I need to correct about this. Okay. Because, of course, A, B, and C are the unknown parameters. You're going to have numbers for all your y's and x's. Those numbers go into this matrix and this matrix in the way that we've done. Fairly straightforward. Of course, in this case, you won't have A, B, and C. You'll understand that when you reduce this equation to 1, 0, 0, 0, 1, 0, 0, 0 here, this is going to be your value C, and this will be your value B, which will equal this. Your value A will equal whatever number you end up with here. And we've been through the details of that. So make sure we're good on those details. So this will be it. Problem. No, I could ask you to reduce the matrix or to use elimination with the system or to write it out as a matrix equation, in which case you wouldn't be able to solve it because you have no idea how to invert a 3 by 3 matrix. I could tell you in a little practice you could do it, but it'd be hard to do it without making little mistakes like that. Okay, so what we end up with is values of A, B, and C. So now we can graph the quadratic equation. Okay, well, let's talk about graphing quadratic equations and solving quadratic equations. Graph a quadratic function. How do we graph this equation? Okay, now it's entirely possible. Okay, well, somebody came up with the idea, well, find the intercepts. You always want to find the intercepts if you can. Okay, that goes back to how you graph a polynomial or rational function we need to talk about, okay? But first we want to refresh our memories and how do we graph a quadratic function, okay? So start by finding the intercepts. Well, you might have x-intercepts and a y-intercept, in which case you have 3 points. It's fairly easy to sketch the graph. You're not going to be totally accurate. Probably going to be more accurate than I was with this first attempt. Anybody'd be more accurate than that. Okay. But we find the intercepts. Okay. What's the next critical thing that we do when we graph a quadratic function? And I just thought that I was not another line pop up. This needs to be part of your picture of the whole universe. Okay. There are many things in the universe that are more important than exponential and quadratic functions. Power functions are in there too. Okay, linear functions, of course. And then you get the polynomial and rational functions. They're important, but not as basic as these. Okay. At least in the physical universe. You find intercepts. I'm going to say, find what the quadratic formula tells you. What's a quadratic formula tell you? Okay, well, here's a quadratic formula. Gives you the intercepts. That's not y, it's x. And the axis of symmetry. And I'll put a closest thing I got the red circle around this. I'll put a light circle around this. As I've explained a number of times, but it's something that's a little bit hard for people to totally grasp and remember all the time. But negative b is halfway between negative b plus and negative b minus this square root of the discriminant, okay? So it's halfway between the zeros. It's equidistant from the zeros. X equals negative b over 2a is a vertical line that's symmetric with respect to the zeros. Since the graph of y equals x squared is symmetric about the axis of symmetry, about its axis of symmetry, then the vertex lies on the axis of symmetry. It's not a bunch of formulas to remember. There's only one formula you really need. You have the intercept, you have the axis of symmetry. The vertex is on the axis of symmetry, which means you know it's x coordinate. This x equals negative b over 2a is the vertical line that constitutes your axis of symmetry. You plug that value of x into the function and you get the y value, and now you get the vertex. You always have the y-intercept. If the vertex is below the y-intercept, then the graph has to do this. If the vertex is above the y-intercept, then the graph has to do this. Okay? Now, vertex will be below if it happens to be negative, it'll be above if it happens to be positive. And that goes back to the transformation picture. And the quadratic function is really the one that I think best illustrates how transformations work. So, your vertex is HK. So, y minus k equals 8 times x minus h quantity squared. That's vertex form. If you expand this square and bring all your numbers together, the function you get here, and solve for y, you're going to get the same thing you started with. And I might well ask you to do that. Just a full circle to help you understand the mathematical thing a little more deeply. If you can't get the whole circle, well, if you get most of it, you're not going to lose too many points. But if you want to make an A, you probably ought to be able to follow the instructions I'm giving you. Okay, which just says, okay, here's your function. Find the intersection of the vertex, write it in vertex form, and then expand your vertex form to show that it's the same as the original. All those steps are very easy. And I would spell it out for you. Unless I wanted to make it an extra credit problem, in which case I'd just say, okay, show me the full circle. Okay. But I can't expect everybody to be able to do that. One of the things we're trying to learn in this course is how to follow procedures. So if you get a slightly unfamiliar procedure, one thing that I'll tend to test for is, can you follow that procedure? If every step is something you know perfectly well how to do, can you put it all together and actually even tell me what that means? It's a kind of a high bar at the level of this course, but I like to see who can do that. Okay, and of course I reward you with grades if you can. So I could start with 3 points. Say, okay, tell me what the quadratic model is. You know, write out the 3 equations, solve them. And if I did that, I would give you a hint that would allow you to quickly reduce your 3 equations to 2 equations. And I can expect you to solve 2 equations and 2 unknowns at any time, just using elimination or matrix methods. Okay. And well, I could theoretically ask you to do that and then show me the graph of the function. Because once you've done that, you know what A, B, and C are. You can find your vertex. You can find your zeros. Okay, so if I gave you these 3 points, now the simplification I give you is if I gave you 3 points and asked you to do this, one of the points is going to be in the y-axis. One of the points is going to be your y-intercept. And it gets really easy to reduce that to 2 equations. I would tell you how. I'm not going to tell you right now, but you necessarily remember. I'm also going to say that, you know, for 20 years, I taught a distance course that I developed. Okay. Very first thing I asked people to do in that distance course was this. Okay. Because I assumed that everybody who came out of an Algebra 2 course knew how to solve simultaneous equations up to 3 by 3. It wasn't even something we taught in a pre-calculus course. It's something that was expected from an algebra course. Of course, I found out that most people couldn't do it, but a lot could. And that was kind of the first hurdle in the course. That's kind of an opening shot that told people, if you're in this distance course, you better have the background. And if you can't do this and can't learn to do this, then you probably ought to find somebody's easier distance course. Okay. So this is a good way to start out the course, but we just can't do it anymore. People don't learn anything in Algebra 2 in most cases because too many people are put into Algebra 2 courses and everybody has a class. There are other opinions and I respect them, but respectfully disagree. Okay, well, I'm off my soapbox. Okay, here's what you have. Okay, so let me just list out the question. Once you have the vertex formed, how do you graph it? Okay, y'all are making me happy. Everybody told me the correct basic function. Okay, and I expected you would, but I'm always relieved. Okay, because we're dredging up stuff we haven't talked about for a while. And it shows me you have some muscle memory or something like that, brain muscle memory. Okay, and of course, this is something that we really emphasized at the beginning of the semester, so I'm gratified that this much of it is stuck with you, okay? And it's to your credit, because you've been working hard. I'll take a little credit for beating it into you early, but you're the one that allowed it to be beat into you, okay? You could have fought back. I'm not that hard to beat, but of course, if you beat me, then you don't do that well in the course. Okay, so how to graph vertex form. Okay, so we know that it's transformation of y equals x squared. What are the transformations? The transformations, and exactly what are they? Okay, thread we're on here is what are the transformations? Okay. Vertical stretch is A, horizontal shift is negative H. We discussed quite a bit why that stretch is negative H. We might talk about that some more, but you might need to review that. At least make sure you know that you're going to know it better if you remember why. And it's just that X has to be H units bigger to give you the same value if you're squaring X minus H. Okay. I'm not going to write that down. Partly because I don't have room. Partly because something you ought to take my advice on and make sure you remember, okay, and understand if possible. Okay, so there it is. Now you just take the points of your basic y equals x squared graph, points negative 2, 2, negative 1, 1, 0, 0, 1, 1, 2, 4, as well as negative 1/2, 1/4, 1/2, 1/4 to get the shape. And then take each of those points and you vertically stretch it. Then the horizontal shift, vertically shift. You can do those shifts in either order, but you have to do your stretch first. Okay? And there's your picture. Now in the 161 class, we're going to go on and probably today, but maybe not till Thursday, talk about graphing polynomials and rational functions. Something that people didn't master as well as I'd hoped, although some of you did quite well, okay, on the midterm. But we want to develop these pictures and obtain some idea of why we do that. Now just comment on something. What if we have 4 points? Well, if we have 4 points, if the 4 points were here, here, and here, there's no quadratic function that goes through those 4 points. There's only one quadratic function that goes through these 3, and it doesn't go through this one. Okay? If you have 4 points, you'd use like 1 higher power, polynomial of 1 higher power. This is polynomial of power. Polynomial. Look, this is, I don't know why I'm having trouble talking. This is a polynomial of degree 2. Okay, highest power is 2. Okay, so if you have 3 points, you can use a second degree polynomial. Polynomial of degree 1 is just y equals mx plus b. Okay, so that would just be like our y equals bx plus c if you want. Any form that's linear. Okay, and if you got 2 points, you can fit it with linear polynomial. You can write 2 equations, solve by elimination. If you got 3 points, you can do a degree 2 model. And you get 3 equations. Okay? If you got 4 points, you can do a degree 3 model. which would be like ax cubed plus bx squared plus cx plus d. Now, if I want to get into that, I'll write it out. I just want to give you the picture that you can exactly fit any number of points by using a polynomial whose degree is one less than the number. So if you got 10 points, you could use a polynomial of degree 9, ab to the 9th plus, et cetera, okay? And you would exactly fit it. It's not generally a good idea to try to do that beyond about the cubic equation in most cases, the degree 3 form for 4 points, because you end up with a polynomial that has to wiggle around a lot and doesn't really have a usable form. That's kind of a neat thing to look at. I might even do an example of something like that. Several things I'd like to put on the test. It could be that I have a whole page of problems like that and say, okay, any one of these is worth some extra credit. So if one of these makes sense to you, ponder it. So what would you do if I gave you 4 points? You'd have to add a degree here. You'd have to do x cubed plus bx squared plus cx plus d. Probably not going to write that out for you. Probably reward you for actually paying attention to the video and paying attention in class. But if you miss it, it's not going to hurt you. Okay, with that, we're just about out of time. And this is probably a good time to stop anyway, so we'll go on and maybe flesh some of this out, or maybe flesh out stuff that we did in last week's first review, okay?
Yes, and there may be.
All right. Extending what we did last time, we're going to talk about how you do an exponential model, how you do a linear model, which you ought to know in either case, or power function model. And then what you need to know about exponential functions, growth rate, factor, and so forth. And then how you do a quadratic model given 3 points, which we haven't done, which is an extension of what you do for a linear model. And then how all that leads into graphing a quadratic function, getting vertex form, and graphing by transformations. Okay, we drug that out of people last time. This time I'm just going to tell you about it. So if you need to have it dragged out of you, just pretend you were in the last class and go through that video. And every time I tell you to do something, do it. Okay? Then I'll tell you how. That's a good way to learn. We don't have time to do that in here. That's why we have the support course. Okay. So the first thing I ask people to do is an exponential model given 2 points. That's draw a picture, any 2 points, as long as they're on the same side of the x-axis, you can get an exponential function model. And the way you do that, and the way you do any model, is you take the coordinates of your points and you plug them into the form of that particular model. So you got to know the form of an exponential model, the form of a linear model, the form of a power function model, the form of a quadratic model. Okay, those pretty much the 4 big ones. And then if you know how to do those, there are other models that follow very easily. Okay. For an exponential model, you can do it with 2 points because the form of an exponential function is either y equals ab to the x, or y equals a times 2 to the kx, or y equals ae to the kx. In any of those cases, there are 2 parameters that you don't know and 2 things that you do know if you have 2 points. The things that you do know are y and x for each point. Each point, you plug in y, you plug in x, and you get an equation. If you've got 2 points, it gives you 2 equations. Now, you're used to doing that. You know, you've done it, especially with linear functions, but we've also done it with exponential functions, and open math has done it with exponential functions. So you plug x and y in, take 1 point, plug it in, you got an equation. The only things that are unknown in the equation, if you use this form, are a and b. Plug in the other point, you got a y and an x. The only things that are left unknown are a and b. Now you've got 2 equations in the unknowns, a and b. How do you solve those two equations? Well, you solve one of them for A. I say eliminate A using substitution. In other words, solve one of them for A and then plug that solution into the other. Okay? So we've done that a number of times. You know how to do that. And if you don't remember how to do that, make sure you review it because it's almost guaranteed to be understood. Okay. Now, you can do the same thing if you got a linear model. You got 2 points, and it doesn't matter where they are. You can find a linear model. The form of a linear function is ax plus by equals c. You got to know that form, or you can't get your 2 equations. Okay. Now, this is a form that works for elimination, and elimination is what we've been doing with matrices and everything here at the end of the semester. Something we digressed to do a fair amount of at the end of our last class. Okay, so if you put the x and y in, put x and y from one point in, you get some number times a plus some number times b plus some other number. So like you get 2a plus 5b equals 12. You put the coordinates of the other equation in, you get maybe 7x minus 3y equals 5. If you got 2 equations like that, then you can solve them. You can solve them by elimination. You can solve them by substitution. You can solve them using an augmented matrix. You can solve them using a matrix equation, except you don't know how. But you write out the matrix equation. And then if you're out there in the real world and need the solution to that matrix equation, just ask Wolfram or just about anybody. There are all kinds of calculators out there that'll do that for you. I could actually at this point explain how you invert a matrix and do all that stuff, but it goes a little beyond the scope of what we do in this course. Actually gets a little bit into what we do in a linear algebra. Okay, so you got the linear model. Give them 2 points, you get 2 equations. You solve for A and B using elimination. We'll do examples of all this stuff. Okay. Because I'm going to go through these ideas quickly, and then we're going to do some examples. Power function model, y equals ax to the p. That's not a model that Open Math has stressed. It's not a model that I've stressed, but it's a model you should be able to use. But if I was to put it on the exam, I would almost certainly say use the model y equals ax to the p. Okay? If you plug in your values of y and x, you're going to have 2 unknowns, a and p. Well, you substitution, solve for a, substitute in one equation, you solve that in for a in the other equation, and you've got an equation in just x that you can solve. Might be an exponential equation that you have to change to logarithmic form. In this case, it would be because the power p is an exponent. You have to find the power p. But that doesn't matter. You just write out the equations. Anytime you give 2 points, you can write out the equations and solve them. If it's this, you solve by substitution. If it's this, you solve by substitution. If it's this, solve it by elimination. You got to know the difference between substitution and elimination. Substitution, solve for one variable, solve one equation for one variable, plug it into the other. Elimination, add multiples, eliminate variables. Okay? Or reduce matrices. That's the picture. Now, it turns out if you're given 3 points, because I do some stuff here, we'll go over to give them 3 points. If I give you 3 points, you pretty much draw a parabola through those 3 points. Okay? Now, you notice I had these 3 points, and I tried to draw a parabola and put a question mark next to my result because it was really bad. Okay? The reason it was really bad was I was trying to keep going up after I got to this point, and really the quadratic model goes through these points, probably peaks, maybe even somewhere around the y-axis, although I didn't set it up that way, so the way it ended up being drawn. Okay? It almost certainly doesn't peak at the highest point. If I give you 3 points, peaks to the left, it peaks to the right. And you can tell by, can you draw a nice symmetric parabola? And it's important to be able to draw that to give you a visual of what it is you're doing. Okay, so I'll talk about this stuff in a minute. But we're going to go on with this idea. Quadratic model given 3 points, you have to have a model. You have 3 possible models over here. You know, your unknowns would be A and B here, A and K here, A and K here. You have a different value of K for this form than you would for this form. But you'd have 2 unknowns. You'd have to solve for them by one method or another. And maybe in this case, you have to change the logarithmic form. If you use this, you don't. Okay. So you've got a form. Here you've got a form. You got to know this form. You got to know this form. I would give you this form. I ask that question, and you got to know this form. That's obvious. And it's something that people pretty much knew on the midterm. It's been over a month. So you're losing track of it. So that's why we're reviewing. We're trying to bring back all the stuff we did before midterm in one package. Especially, not going to probably talk about it today, maybe graphing polynomials and rational functions and simultaneous functions, okay? Because those are things people did bad on. Rational functions, everybody's terrible with rational functions. Polynomial functions, yeah, not as bad. On the whole, pretty good midterm, except for those 2 things, okay? Okay, so this form, these 3 forms as needed, okay? And you should know all 3 forms. Once you know the form, if you've got 3 points, you plug the points in. You plug the x and y coordinates of this point in here, and it gives you an equation. You plug in the x and y coordinates of this point, and it gives you another equation. You plug in the x and y coordinates of the 3rd point, it gives you another equation. Now you've got 3 equations. Your unknowns are A, B, and C. So you can solve those equations by elimination. And you have problems where you solve 3 equations by elimination. Most likely, if I was to give you 3 points and ask you to do this, one of the points would be on the y-axis. So you can immediately reduce your 3 equations to 2 and then just solve the 2 equations, okay? I would even give you a hint as to how to do it since we haven't really done this. If one of the points is on the y-axis, then you've got 3 equations with A, B, and C. You just subtract one equation from another, and C goes away. Subtract another equation from a different one, okay? Or subtract one of those equations from the one you didn't subtract it from, okay? And C goes away. And now you've got equations of A. Very simple. You have to do it to see it. If I gave you step-by-step instructions, well, one of the things you want to learn in this course is how to follow, 2 or 3 steps when you know how to do each step. If I spell out the steps for you, and I expect you'd be able to do it. Actually, I'm pretty confident you'll be able to do it if you can do elimination. Okay. And if you can solve a system of 2 equations. Now, solve by elimination. Even if it's 3 equations that aren't easy to solve, theoretically you should be able to solve it. But I probably wouldn't give you 3 randomly generated points and ask you to do that on an exam. It takes too long. I want to see that you know how to do the steps. That's it. Okay. So you're going to get 3 equations. You can use elimination or you can use matrices. If you use matrices, your augmented matrix is going to look like this because you've got 3 equations with 3 unknowns. You're going to have 3 numbers here, and then on the right, you're going to have the 4th number because every equation is going to have some multiple of A plus some multiple of B plus some multiple of C equals Y, some number for Y. the number for y would go over here because it's on the other side of the equal sign. The three numbers, coefficients of A, B, and C would go here. I think you know that. Okay. So it's going to look like this. If you do it as a matrix equation, you're going to have a matrix here multiplied by A, B, C. And you're going to have three numbers over here. Okay. These are the three numbers on the other side of your equal sign, your three y values. These are the numbers you get for A, B, and C, for x squared and x. Okay. I'm going to have, these are all going to be ones, because you just got to see. No, I'm not going to, you might not understand everything I just said, but do an example and then come back and look at what I said and it makes sense to you. Okay. Now, this leads to, I could actually give you 3 points, ask you to solve all this stuff. You'd probably make a mistake. Okay. But I could ask you to do that. Then graph the thing. Now, you might have already sketched the points and sketched your graph, so you have an idea what your graph ought to look like. It'll be neat then to be able to go over here and graph the equation and see how close you got. Okay. If I ask you a question that long and that complex, probably be broken into 2 questions in there. Okay. And I'd probably manipulate it so that the solutions come out with like whole numbers or easy fractions. When you get into this form, though, what I might do is say, okay, here are the 3 points. This is the form, this is your quadratic equation, your quadratic function. I give you the quadratic function, but say, tell me how you would get it from these 3 points. Okay. Then the next problem might well ask you, okay, now tell me how you would graph it. Make sense? Maybe, maybe not. Bottom line, you should be able to plug your 3 points into this form and get 3 simultaneous equations with a little bit of instruction. Just a broad hint. You should easily be able to solve the 3 equations using whatever method I might specify. Okay. I might well say something like, okay, solve it. Show me how you'd solve it using elimination. Show me how you'd solve it using augmented matrices, and show me how you'd set it up using a matrix equation. I could ask you to do all 3, any 2 of the 3, or any 1. And I might ask you to show me how it would be set up for all 3, and then use the method of your preference to solve it. All kinds of ways I can pose this question. Okay? But it's no different than this question, or this question, or this question, except you get 3 equations instead of 2. Okay. So given 3 points, you should be able to set up equations and solve them if I'm merciful on the 3 points that I gave you to make it simple, to reduce it to 2 equations. Okay, I've said that about 6 times. Now, I could also ask you to graph a function. Maybe it's a function you get when you do this, or maybe it's a function I give you to do. Okay, it might even be the function that solves this. So you can see whether you got this right or not. I'm looking at your steps more than your accuracy when we do that much arithmetic. There it is. Okay. How do you graph a quadratic function? Well, again, don't have time to drag the answer out of you. I'm just telling you, but then we're going to look at examples. Graph a quadratic function. Well, to graph any function, if you're given the function, find all the intercepts you can. How do you find the intercepts? Well, you set the function equal to 0. Okay? That gives you your x-intercepts. That works for polynomials, works for rational functions, works for shifted exponential functions, works for linear functions, works for quadratic functions. Okay? You always find the intercepts. And you can always find the y-intercept unless the y-axis happens to be an asymptote. Okay? Which it might be for a rational function. Other than that, though, you can always find the y-intercept. And there's only one y-intercept for the function because the function is single value, passes the vertical line test. You got to know that. Okay, so you find the intercepts. That's not necessarily enough when you're doing a quadratic function. You're going to have a y-intercept. You don't necessarily have x-intercepts. The graph of a parabola could lie completely above the x-axis or completely below, in which case it doesn't have any x-intercepts. Well, how do you find the intercepts of a quadratic function? You should know. To find the x-intercept, what do? You set y equal to 0. To find the y-intercepts, what do? You set x equal to 0. You can't set x equals 0 unless you have a function with a vertical asymptote or an undefined value at 0. You're going to be able to plug in x equals 0. Okay. Well, then what do? Well, it's been a while. Everybody was pretty much able to do it in the exam, midterm. But we find the axis of symmetry. Okay. And the clearest way to indicate that without completely saying it is to write out the quadratic formula and circle the negative b over 2a. Anytime you write out the quadratic formula, you ought to circle the negative b over 2a. And remember that that's going to be the vertex. Hopefully even remember why it's the vertex. Why is it the vertex? It's the vertex because negative b is halfway between negative b plus the square root and negative b minus the square root. Halfway between this plus this and this minus this is this. And halfway between the zeros, that's where your axis of symmetry has to be. If it's symmetric, it's got to be the same on this side as it is on this side, meaning if you have a 0 on this side, there's got to be a 0 on the other side at the same distance, telling you it's halfway between. Okay? Think about that. Okay? So, get the intercepts and the axis of symmetry from the quadratic formula. So this formula gives you the intercepts, it gives you the axis of symmetry. The vertex is on the axis of symmetry, so you can find the vertex. Once you found the axis of symmetry, find the vertex. That's the most important point of all on a parabola. It's a point where it hits its maximum value or its minimum value. And often you want to maximize or minimize a quadratic function in applications. Example I've used a number of times is if you use your basic simple quadratic model for profit versus selling price, you want to get a graph that looks like this, and your profit occurs right up here at the vertex. If you know the coordinates of the vertex, it tells you the price, which is your x coordinate, and it tells you the profit, which is your y value. Now that's a model. Hopefully you've got good information in your model. No model ever works perfectly well. Okay? You know, the models they're using to put that spacecraft in orbit around the moon, and it's in the process of adjusting its orbit to come back to Earth, which is good if you have astronauts on it. And if you want to study reactors and other stuff, you really want it to land safely. Okay? Those models work really, really well because there's no stuff out there to interfere with the model. Just this gravitational force and that gravitational force, and then you do some pretty complicated mathematics. You figure out when to burn your engines, okay, how to design your orbit, and you figure all that out in advance and then make little adjustments. If you're doing a profit versus selling price, there are more unknowns out there. You know, like what happens to consumer preferences between the time you make your model and the time you're trying to make your profit. Okay, what happens to consumer willingness to spend, which is going to affect your model. You try to predict all that stuff. It gets very complicated. So going into business, there's things you want to start thinking about. And the quadratic model is a good place to start. There's a whole lot of information in that model. Now, for engineering, nobody's going to be an engineer. Yeah, some of you might be, and you might just change track, or some of you have the ability to do that in the background. If you ace this course or make a strong B. and really want to be an engineer. I don't know why anybody want to drive trains for a living. That's what engineers do, right? They drive trains. And they got to stay on the tracks. What is there driving a train? Well, yeah, you go over a mountain, you better not have the train split in two because of this downhill on this side and downhill on this side. And yeah, there's actually some significant engineering there. Okay, well, you don't just drive. You don't have a steering wheel. Can't go off the track. It is fairly complicated. Okay, well, the driving trains thing aside, most of them are probably not going to choose to become engineers. Tough path. Although it's quite a bit or more. Okay. Back to reality. Once you know the vertex, you can write out the vertex form. And you should know the vertex form as well as the general form of a quadratic function. Where do I put the general form? Yeah, there. There's your general form, okay? This is general form. This is the vertex form. At this point, once you get it into vertex form, you can simplify this whole thing and put it back into this form and see if you got it right. So if I ask you to do this, I'm probably going to ask you to, okay, simplify this and see that it's the same. If it isn't, it means you made a mistake. If all your steps are right and you made a mistake, you still get substantial credit. If you made a mistake and won full credit, you probably better go back and figure out what you did wrong. If you have time and don't sacrifice a bunch of points in another problem that you can't even start all your time. There are no time limits, but the time limit is testing center does close. Okay. You got to watch out. Okay. So there you have it. There's kind of a full circle thing that goes here, kind of a full circle thing that can start here and end here. Okay. And it could even go a little further. How do you graph the vertex form? This goes back to the most fundamental things, which are your basic functions. Because this is just a transformation, stretching into shifting transformations of your basic quadratic function. What do you do with that? Well, first of all, how many transformations do you have in this form? Well, x is replaced by x minus h. So you have a horizontal shift of negative h. Remember, why is it negative h? I'm going to talk about it right now, but review that. Vertical stretch is your a, and your vertical shift is k. If I add k to both sides, I say I've got a times the quantity x minus h squared plus k. Okay? So that if you have y equals x squared, and your a f of x minus h plus k is, well, in this case, it's a lowercase a. It's this, which is just another version of this, considered equal to y. You should understand this function notation. You need to understand function notation. This is the general function notation for any basic function or any other function for that matter. If you're shifting it h units in the x direction, k units in the y direction, after stretching it, I factor a in the vertical direction. Okay? And it could be a compression phase less than 1. So I use the terminology of the open math that works. I'd like to just use one word. Okay. It's stretched by a factor less than 1 is compression. It's stretched by a negative factor is reflection across the x-axis. But you can think in terms of compressions or stretches. You can think in terms of reflections. That's all good. And whichever way you prefer to think about it, it still looks like this. Okay. If a is less than 1, it's a compression. If a is negative, it's also reflection. Okay. Well, there it is. 25 minutes. Now we're going to work out some details. All I've got to do is find a board. That's something more that I want to erase. That would be this. So what I'm going to ask you to do first, draw a set of coordinate axes. Put 2 points on it on the same side of the x-axis. Could be above, they could be below, but they got to be on the same side of the x-axis. Second one doesn't have to be higher than the first. And use one of these 3 forms to write out your system of simultaneous equations you're going to solve. While you do that, I'll clean this board and we'll be able to slot some stuff down. Yes, I've thought about using an ad blocker, but I need the computer to run fast for a lot of stuff I do, and ad blockers really slow it down. I could also go in and disable pop-ups and enable it, disable it, enable it. Sometimes I just need the pop-ups. If you need them, I don't want to have to go through that. It'd probably be the easiest solution. It'd probably be a good thing to do before class and then after class. But sometimes you do things in class. I don't know. Okay, nice suggestion. Though. Thought about it. Asked about it. Our administrator said, if you want to. Okay, so over here. So we got the y equals ab to the x. So let me go ahead and put a couple of coordinates down here. You might not be able to read it, but I'm trying to keep things compact. Minus 2, 7, and 5, 1. Make it 5, 2, because I don't want to use points. So form y equals ab to the x. At this point, y is 7, the x is -2. So we get 7 equals a, b to the -2. Here, x equals 5, y equals 2, so we get 2 equals a, b squared. Okay, now it's very easy to solve that. Solve this equation for a, you get 7 b squared. Then plug 7b squared in for a, and you get 7b squared times b squared, which is 7b to the 4th equals 2. Divide both sides by 7, you get b to the 4th equals 2 sevenths. You can take the 1/4 power of both sides. I'm not going to take time to do that. Right now, I might write it down very quickly. I'm not going to explain it because we did it in detail several times. Okay, so you should be able to review that. I think open math also addresses. We're looking at how you start the problem. I'm going to have to assume you can do the algebra. It might be I go back and do the algebra. If we use the form y equals a e to the k. So let me just write it down here. B ends up being equal to 2 over 7 to the 1/4. Solve this for a, and then you plug it in here. Okay, so if you understand my arrows and my explanation, there we have it. B equals this, and then you can take this back in here and get it. That's the process. If you don't understand that, review. Okay. I put that down there so you can see that what happens if you use this form is you just have to solve an exponential equation. You have to just take the same power both sides. In the last step, you get b to the 4th equals 2 sevenths. Take the 1/4 power both sides, you get b. should understand the laws of exponents and understand why that works. Because laws of exponents are extremely important, but we important to needs. If the form is this, you're going to get 7 equals a e to the negative 2x, negative 2k. And you're going to get 2 equals a e to the 2k. Well, you do the same thing. You solve this for a, you put it in here, and you get all right, I'm not going to write the solution because in a couple of steps, you get 2 equals 7 e to the 4k. How do you solve 2 equals 7 e to the 4k? Let's take a minute because this gets into solving an exponential equation. Here's an exponential equation. So I'm going to write this out a little bit so you can read it. Let's say you get okay. Take a minute. Show me how you solve that. Okay, I wrote down, I didn't write down this equation. I wrote down something similar to this. I had the wrong exponent. We're looking at the equation 2 equals 7 e to the 4k. So you don't have an a in the equation. You've eliminated a, and you pretty quickly get that. Now remember this equivalence, the inverse function equivalence for the exponential and logarithmic forms, right? You got to know this and practice using it. And that's what you need in order to solve that equation. Some of you already have the solution. Some of you are having trouble getting started. You get a solution very quickly if you convert the form. So people need to be real clear on how to use this equivalence. Okay, it changes this equation to the form e to the 4k equals 2/7. Okay, which then becomes k equals the natural log of 2/7. Natural log being log base e. So you probably write that out log base e if you were doing this literally. But you have to know that log base e is the natural log. Okay, so that's one little twist. Now, if you use the k times 2 to the kx, you'd have a log base 2. Instead of an e, you'd have a 2 here. And it'd be log base 2 instead of log base e, which is natural log. Okay, but you have to know how to solve this equation, whether it's an exponential form or has the base of 2 or any other base. That could be a totally separate problem. It doesn't have to be in the context of solving the exponential model. Okay, so make note of that. That's absolutely essential. You're going to see it. You're going to need to use this. You need to know how to use it. Okay. So you get 2 equals 7 e to the 4k. And that gives you k equals natural log of 2/7. The k would be like the natural log of 2/7. You punch that into your calculator, you have natural log function on any calculator. And then divide that by 4. Straightforward. Okay. Okay, well, that's what we do if we want an exponential model. But what if we wanted a linear model through these points? But what if we use this form? Well, if we use one of these forms, we get an exponential model. So if you're asked for an exponential model, you have to know to use one of these forms. Okay. I might say, solve this, find your function using any form you want for the exponential, any exponential form. Can't use just any form for the exponential. You have to use an exponential form for the exponential, but those are the three main ones. Okay. And I've commented, this is a form you can use in calculus. It is easy to use this and this. So you kind of want to get used to it. But calculus class, if you take one, will refresh it. So if you want an exponential model, you're not going to use this. Now, I commented in the last class, I'll comment now in dual enrollment classes, even the top students will typically do a linear model if they're given 2 points. Even though it says do an exponential model, they don't know what exponential means. How do you get out of a pre-calculus class not knowing what exponential means? Well, I'm going to do my best so you're not getting out of this class unless you know, okay, for your own benefit. People use these terms incorrectly, and they're terms that you see even in news articles and stuff, okay? And if you don't understand them, you don't understand what you're reading, and you make bad decisions. If you're making any decisions based on real information. So if you want a linear model, there are other linear models. Y equals mx plus b is okay. Okay. Any valid linear model will work, but this is the model that works with elimination. So that's a model that we're going to use as a preferred model. And it's a model that makes it easiest to find your intercepts. If you want to find the y-intercept, let x equals 0, then you just got y equals b over c. Okay. And if you want your y-intercept, your x-intercept, you want y equals 0, that goes away, you get ax equals c. Your x-intercept is c over a. Okay, and this translates into things you do with conics and stuff like that, but something else to do with osmosis. And when you do, if you know this form, if you do need it, you're a good start. Okay, so you get 2 equations, solve for a and b using elimination. Well, that's really easy. Okay, use the forms. These are exponential. They're equivalent. Exponential model. If we use the form ax plus by equals c, write down the equations you're going to get for those points. And keep in mind that this ain't exponential. Doggone it. Okay. It's not a power function. It's not an exponential function. It's not a quadratic function. No. Write down the equations. You know how to solve them. Just write them down quickly. Okay, now I've changed the form we want to use here because I just realized the form I gave you has 3 parameters. We get around that and letting c equal 1 in both equations, but I'd have to explain why. Okay, so instead, we're going to go ahead and use y equals mx plus b form. So you can easily write your equations. Okay, well, we're going to change the form as I did. You can deal with this form, but again, there's a complication that you really don't need. since you can do it easily with this form. In this form, you get 7 equals negative 2m plus b, and 2 equals 5m plus b. Okay. Now, what variable is going to be easy to eliminate? Is it going to be m or b? I would eliminate b because it has the same coefficient. If you just multiply one of these equations by -1 and add it to the other, it's going to work. Or if you're careful, subtract one equation from the other. Okay. So I'm going to use multiplication by -1. So I'm going to get -7 equals 2m minus b, 2 equals 5m plus b, equation 1 plus equation 2 gives us -5 equals -3m. M equals 5/3, etc. And the etc. is you take 5/3 for m, put it back in here, and you find b. So I'm not going to go through all those details, but that's how you do elimination. Alternatively, you could write this as, first of all, if we want to translate it into an augmented matrix, we're going to put the number on the other side. Now we're going to write this out as -2m plus b equals 7. Just switch the two sides. 5m plus b equals 2. And then we have the augmented matrix, -2, 1, 7, 5, 1, -2. And that matrix is very easy to reduce. Okay. For the matrix equation, and you might have to review a little bit, but the matrix multiplication is simple. -2, 1 times mb is -2m plus 1b, which is -2m plus 1b, right? And first row multiplied by this has to equal the first number in this row, that's 7. Okay, then if you multiply the second row by this, you're going to get 5m plus b, that's got to be equal to -2, there's your equation. Okay, well, now my big point is, this is linear, this is exponential. As if you're exponential, do exponential. Fast if you're linear, do linear. I might ask you for both and identify which one is which. I could even ask you to do the power function, but I'd have to give you the form. I don't expect you to remember that form, although if you do, that's great. Okay. And again, the solution is straightforward in each case if you know how to do substitution and know how to do elimination. Okay. Now, right down the section we would have a quadratic model. Now, if you did a quadratic model for just 2 points, you wouldn't have enough information. You'd only get 2 equations. A quadratic model is y equals ax squared plus bx plus c. Just like you got an m and a b here, or a and a b for this form, or an a and a k for this form, you only had 2 parameters that you needed to solve for. Here, you've got 3. So we're going to need 3 equations. So just as an exercise to make sure you understand what we mean by using an appropriate number of points to get our model. I think it's kind of important, right? Let's take these 2 points. Negative 2, 7, 5, 2, and 7, minus 6. That's not accurate. Let's make it 7 minus 10. Quadratic model y equals ax squared plus bx plus c. What are your 3 equations? Okay, so we got 3 points. We want to do quadratic model. All I'm trying to do here is convince you that you can put x in where you see x and y in where you see y. That should be automatic. Okay. So you got the model. Here's your model. Here's a point. X is negative 2, y is 7. We're going to get 7 equals a times negative 2 squared plus b times 2 plus c. Okay. And you're going to get 2 equals a times 5 squared. People want to square the a. A couple people tried to square a. Okay. But no, square is not on a, it's on x, and x is a number. Okay. So be careful, but that's real easy to fix. Well, here's our 3 equations. Now we're going to write this out then as, negative 2 squared is 4. We're going to write 4a plus 2b plus c equals 7. We're going to write 25a plus 5b plus c equals 2. And 100. A plus 10b plus c equals 7. Excuse me a second. Got all kinds of hands in the air. So. Okay, a couple things I need to fix here in my clerical abilities. Down through the floor. Okay, should be minus 2 there. And yeah, 7 and negative 10. So this equation was all wrong. I actually thought about that. You said not number okay. It started to write 49a. And okay, that should be negative 10. That should be 7. That should be 7. So we get 49a plus 7b plus c equals negative 10. All right. Well, that's all fine. Now, what do we do with this? Well, you notice I can eliminate c really easily. And one of these is just c. So I could multiply this by negative 1, add it to this. Multiply this by negative 1, add it to this. And I'd have 2 equations, which is a and b. And then we know what to do with 2 equations, right? Or I could write this out as a matrix, or another augmented matrix. I'm not going to write the matrix equation, but just because we're almost out of time. There's an augmented matrix, and these are ones, not dots. Let's make it look like ones. I think I'd be able to make chalkboard there, but there it is. Okay. Make sense? So it's no different than anything else we've seen. We've just got more numbers and we've got more equations. And we've got a system of equations that easily reduces down to a system of two. We can solve. Okay. Well, now let's just say that we get the model or attempt to estimate this. Let's say we got y equals 5x squared minus 12x. We can minus 17, so there are zeros. Then quadratic formula. Why did I use the number? 20 times 17 is 340. Okay, quadratic formula very quickly tells you that y equals 0 if x is one of these numbers, assuming I got the numbers right. Putting a little red circle around the negative b over 2a, this thing tells me that the axis of symmetry is at x equals 1.2. Okay. The vertex is at 5 times 1.2 squared minus 12 times 1.2 minus 17. That's actually fairly easy to do. It's negative 31.4 and pretty close. Negative 22.4. Okay, I might have done that correctly. I might not have, but let's assume that I did it right. The vertex form, and I'm really running out of room, we're out of time, but it's y equals, well, it'd be easier to read this. But it's your y minus k equals a times x minus h squared. H and k are the coordinates of the vertex, 1.2 and negative 22.4. If I did this correctly. Yeah, that works. Okay, which means that then I transform the y equals x squared by horizontally, well, first of all, vertically stretching by a factor of 5, horizontally shifting 1.2 units and shifting it 22.4 units down. Okay. And we should be in pretty good shape about the idea of transformations, but this is bringing us back. We're kind of working backward through the course. We're all the way back to basic functions at this point. Okay. We see if we take everything we've done and do it in forward order, we see how things fit together, or at least we begin to see how things fit together. Okay. So more on Thursday. And we'll certainly be hitting rational functions and polynomials pretty heavily then.